Tables are expensive because of indirection latency and because of storage. So one of the proposals that we have is a linear mapping wear leveling, which we call start gap, which was introduced in Micro 2009. And the idea is fairly simple. Essentially, you can do wear leveling by moving one line every 100 writes, let's say. So to do wear leveling, you need two registers, start and gap, and one extra line to do movement. The way you do wear leveling is, let's say you have 4 lines A, B, C, D. After 100 writes, you move one line, say line D. The way the gap line is moved is so you simply copy the contents of D into the gap line and you move the gap pointer. And you do this again. Let's say you move C, you move B, you move A, and then you move D. This picture, the order is again A, B, C, D is just rotated by 1. And the start register keeps track of where the start location is. The advantage of this scheme is that getting the physical address is quite simple. You take the logical address, you add start to it. If it is greater than gap, you add 1 to it. So the latency is just two adders. The storage is just 2 registers, start and gap. You take the gap line from one of the spare lines. And the write overhead, because you do 1 move every 100 writes, it's within 1%. So it's quite low. To increase the efficiency of start gap, we essentially use a randomized address space instead of a normal address space. And this avoids the hot regions and predictability. And with this scheme, you get roughly 97% of the ideal wear leveling endurance that you could get for typical applications. But the problem is, under adversarial scenarios, such a scheme can have very short lifetime. Let me explain this. Because you move a line, let's say, every 100 writes, if there are n lines in memory, you'll move the line after 100 n writes. N is in the order of millions. Let's say it's 4 million. You can potentially do 400 million writes to a line before the line gets moved. Of course, the endurance is not that big. Endurance is in the range of few tens of millions. So the line will get killed before it gets moved. And such codes are fairly easy to write. You need only about 10 lines of C code to write such a stream that can essentially bypass all the caches and write to the same memory line again and again and again. And this is a problem not just from external attackers, but also from greedy users, because if you want a new machine before your end of warranty period, you can sort of, right before the warranty period, try to kill your memory and get a new machine. So this is a fairly important problem, and several people have looked at it. In the start gap paper itself, what we recommended is that instead of managing the whole memory using start and gap, you split the memory into chunks, and you manage each chunk with a start and gap. And the idea is that the line will move. If the region is small, the line will move before the endurance is reached. There's a table-based scheme as well that has a large number of lines per block, and then it swaps blocks with certain probability on a write to a block. There's one more scheme, security refresh, that was introduced in ISCA 2010. So the key commonality in these schemes is randomized wear leveling. Essentially, when a line gets relocated, it should be very difficult for the attacker to find out where the line is. Otherwise, the attacker just can keep writing to the same line again and again. So what's the problem? The problem is, how frequently should you move the line? Let's say you tune the rate such that the line only, during an attack, you can only eat away half of the lifetime of a line. That's not sufficient, because if you have a large list, randomly if you're trying to get elements, you need only try very few times to get the same element twice. This is what is called as a birthday paradox attack. So you need roughly square root of n trials, and under such an attack, the lifetime is in the order of a day, which is clearly not sufficient. So we need to lose not too much of a lifetime before the line gets relocated. So the LVF should be small. And we did some theoretical analysis, and we found out that to ensure at least half of the theoretical maximum lifetime, before a line gets moved, it should not lose more than 1/64th of its lifetime. What does this mean? To ensure that the line does not lose more than, let's say, 1% of its lifetime, you need to do wear leveling at a much faster rate, at a very rapid rate. For example, for randomized region-based start gap, you need more than 100% overhead. For the table-based scheme from Sesnick, you need 12.5%. For security refresh, you again need more than 100%. These overheads are intolerable because every write will incur one or more writes. Writes are expensive, they're slow, they're power hungry, they take away useful endurance. So it's impractical to have this high an overhead for secure ware leveling algorithms. But we do need robustness. So we need both. We need low overhead for typical applications, yet we need robustness under attacks. So the key idea that enabled getting both of these requirements simultaneously was that what we really care about is for typical applications, our overhead should be low. Under attacks, it's okay to have a higher rate because performance is a secondary concern under attacks. Given that the machine is almost never under attack, you'll get good performance. And when the machine is under attack, you'll have ware leveling at a much higher rate, but performance will get sacrificed, but that's not a concern. So we propose an adaptive ware leveling algorithm. Essentially what a ware leveling algorithm does is it takes a logical address and it has some mapping, it gives a physical address, and there is a circuit, attack detection circuit, that figures out what kind of a stream is going on, and depending on the properties of the stream, it controls the rate. So for typical application, the rate is low. For attack-like application, the rate is high. To identify attack-like applications, we need to first define what an attack is. So we came up with a metric called attack density. Attack density is the number of writes to the most frequently written line divided by total number of writes. So if you're writing to one line again and again and again in memory, attack density would be 1. If you're writing uniformly, and there are n lines in memory, it will be 1 over n. Now, the typical value of n is like tens of millions. So the difference between the highest possible value of attack density and the lowest is like 6 or 7 orders of magnitude. For typical applications, the attack density has a value less than 0.1% because a typical application writes to a large number of lines before writing to the same line again. If it is writing to the same line again and again, it will probably get a hit in the cache, and that write will not be visible to memory. So essentially, this metric correlates with the severity of attack. And because if this metric is less than 1, what it means is that you're writing to several lines, and for each of these writes, the gap would move little by little. And so the amount of lifetime lost will not be that much. To prove that the attack density for typical applications is indeed less than 0.1%, we conducted a very simple experiment. We had a 32 megabyte last level cache, and we kept track of the last W writes that were evicted from this cache. So let's say we want to track the last 1,000 writes. What's the probability that a given write can match any of the 1,000 writes? So we found out that for the last 1,000 writes, the probability that a given write would match any of the last 1,000 writes is very low. It's less than 1 in a million. If there was a line being written once every 1,000 writes, this probability would be like 10 to the power of -3. So for typical applications, the probability of a hit in the last 1K writes is indeed very low, less than 1 in a million. It almost never happens. How is it for an attack? For that, we must first define what an attack is. So inevitably, for an attack to be successful, it needs to do 2 things. First, it needs to write to a few lines again and again. If it's writing to a large number of lines, then a normal ware leveling algorithm can handle that kind of a pattern. Second, it needs to write to those lines large number of times, millions of times. Otherwise, it cannot cause that much damage to those lines. So we analyze several forms of attack. First is a repeat address attack. You write to that line again and again and again. You write to n lines again and again, 1, 2, 3, 4, 1, 2, 3, 4. In a birthday paradox attack, what you do is essentially change the working set of the attack. You write to a few lines a large number of times, and then you just randomly write to another set of lines a large number of times. And the fourth attack is where you take an attack line, you write to it once, and then you insert enough random elements. And then you write to the attack lines one more time. So essentially, in the fourth attack, a stealth mode attack, the attack line is disguised in a large number of lines. So the fourth attack is kind of difficult to detect. So we'll focus on detecting this kind of attack. What's the hit rate for a last 1,000, or window of last 1,000, right? For all of the attacks, the hit rate is greater than 10 to the power of minus 3. For typical applications, it's less than 10 to the power of minus 6. So this hit rate in the last 1,000 writes can clearly separate the two kinds of applications, typical applications or attack-like applications. But this would solve the problem, but this is not a practical solution. Why? Because tracking 1,000 writes and searching them on every write is impractical, both because of latency as well as power. So we need a practical solution. The key insight that allowed a practical solution is that most of the lines would not give you a hit while in the detector. If there's an attacking line, it will be written a large number of times. So if you do things probabilistically, you can converge on a very good hit rate. You can converge on the real value. So we can approximate the hit rate of a large window by a smaller window by just inserting with a small probability. If the line is written again and again, it will eventually enter the detector, and it will stay in the detector and give hits. And this is what we call a practical attack detector. It contains of 16 entries. Each of the entries is just a tag line. It does not require any data line. There are two counters, two global counters, a hit counter and a write counter. Every time you write to memory, you look into this list, and you increment the write counter. If you find a value, if you find the address that you are going to write, you increment the hit counter, and you essentially update the replacement position. And whenever the counters overflow, you compute the hit rate. And pessimistically assuming that only one line is being written, one line is being attacked, the hit rate is, the attack density is similar to hit rate. This is pessimistic because if two lines are being attacked, this will give you a higher hit rate, but that's not a problem. So we conservatively assume that the attack density is just the hit rate of this detector. How does this perform? This graph shows the estimated attack density divided by the actual attack density. Okay. Sure, the projector shut down. So this is exactly the point till where I covered in the tutorial. Yeah, so, I mean, I don't need the slides. The key idea is that if the entry is in the detector, it will take a while for the line to get into the detector, but once it's in the detector, it will give you hits again and again and again. Yeah, so, okay, it's still warming up. You're in a stealth mode attack. You have one attack line and then n random lines, right? So what is that n? That's what is varied here. So if you're tracking a window of 1,000 writes, you could potentially do one attack write and 1,000 minus one random writes, and a window would catch that. It will give you an attack density of 10 to the power of minus 3. And if you have a probability of insertion 1 over 256, that's what you get. Till a window of 1K, you can track. After the window of 1K, the accuracy drops. So essentially, just probabilistically entering the detector once every, randomly 1 over 256, can give you very good accuracy. What is the detection? Because we are entering whenever an access goes, and it's not in the detector, it's inserted with a small probability p, 1 over 256. This graph shows the probability of detection versus the number of attack writes. So within a few hundred attack writes, the probability that the attack line will get detected is fairly high. Given that the baseline system has an endurance of 32 million, even if it took a 32,000 writes, that's negligible amount of lifetime loss. So the detection latency is quite small. But this solution by itself is not sufficient. I'll explain why, how you can trick this kind of a detector. Let me explain what actually happens in the detector first. So let's say you're writing an attack line. So the big arrows are attack lines, the small arrows are random lines that are not being attacked. So when you're attacking a line again and again, the first few times that the line will not get inserted into the detector. After a while, it will get inserted. All the hits after the line gets inserted occurs a hit in the detector. When the attack stops, other lines sort of start coming in the detector, and the attack line will get evicted from the detector. So the detection period is essentially the time that before which the attack gets detected, and the retention period is how long is an attack line retained before getting evicted from the detector, how many random writes are required for the line to get evicted. And this creates a vulnerability. The detection period is about 256. The retention is about 4,000 random writes. What an attacker can do is write few times, write 50 times, and then write 5,000 random writes. What this will do is most of the write will get missed in case the line indeed enters the detector. The 5,000 random writes will essentially evict the line from the detector. And this sort of an attack is quite effective. This graph shows the error in attack density, as the number of attack writes in this kind of an attack is varied for a different number of random writes. So for the best attack, we found that the best attack happens when you write 60 times, followed by 6,500 random writes. And this kind of an attack can make the attack density off by a factor of 9. But this is not as severe. Why? Because you're only doing a very small attack writes disguised in a large number of writes. So the attack itself is quite slow. The attack is happening at 1% speed. So lifetime is about 40% of theoretical maximum. But we still want at least 50%. We can solve this by essentially increasing the retention period of the detector. The key insight here is that if the retention period is large, then the attacker has to write to the attack line a large number of times, and that's fairly easy to detect. How can we increase the retention period? Again, an insight that most of the lines that enter the detector almost never give you a hit. The attack line indeed gives you a hit, so it makes sense to retain the attack lines longer and not retain the other lines. So we essentially use a frequency-based replacement. It's called reuse replacement, and it works like this. When you enter a line, the frequency counter associated with the line is 0. If it gives you a hit, the frequency counter is incremented. The line D here is, let's say, the line under attack. If you want to insert another line, line X, there's a pointer that tells you where to begin your search, and the victim line is essentially the line that has a counter value 0. So let's say if you want to enter another line, X, in the detector, line C, the counter value is 0, it's evicted, and the pointer is incremented. What this does is that a newly installed line will be checked only after all of the other lines have been checked. So this essentially gives some form of time period for the line to accrue a hit. Let's say you want to enter another line Y. Line D, the counter value is not 0, the counter is decremented, and then you check for the other line. It's indeed 0, you install line Y, and then you increment the counter. So essentially what this does is it retains the attack lines much longer than other lines. What a frequency-based scheme does is that it gives you a very high retention period in the order of hundreds of thousands of writes. So this graph shows the retention period and number of 1,000 writes required, the probability of retention. For a LRU-based 16-entry detector, 32-entry detector, 64-entry detector, and a frequency-based scheme, just with 16-entry detector, but the counter values change from 6-bit, 7-bit to 8-bit. So what a frequency-based scheme does is it gives you a retention of about 1 million writes. That means the attacker, if the attacker wants an attack density of more than 0.1%, the attacker will have to write more than 1,000 writes in each iteration. Because the retention period is large, the detector is quite accurate. In this case, instead of being off by 9x, it's off by only, the detector is off by only 25%, 1.25. And again, this is a very slow attack, so it's okay if the detector is not very accurate. So the detector is accurate within a factor of 2. So till now, what we have focused on is developing an accurate detector. How does this help? Well, an accurate detector can enable adaptive wear leveling, tying it back to the original problem. What we have done is essentially we have chosen the option on the right, on your right. Use a low rate of wear leveling until the attack density is 0.1%, and then increase the rate of wear leveling in proportion to the attack detector. What does this do? Under attacks, these evaluations are for lifetime. The configuration has 4 million lines, 32 million endurance. Under a uniform write, this system will give you a lifetime of about 8 years. Under the most severe attack that we considered, the lifetime is about 5.5 years. As the number of attack lines increase, as the period reduces, the overhead reduces as well. Under a stealth mode type of attack, your lifetime is still more than 7 years. So what this does is it gives you a lifetime in the range of years, even under attacks. What happens for typical applications? For typical applications, their attack density is less than 0.1%. So what you have is a scheme that is similar to the original start gap, which gave you 97% lifetime, and the overhead of less than 1%. To conclude, wear leveling should be robust to not just typical applications. It should be robust to attacks as well. But that's a conundrum. Essentially, the rate has to be very high for security, but the rate should be very low just because of overhead reasons. And what the attack detector does, it allows you to get both. Low overhead for typical applications and robustness for under attacks. What I've shown is just using attack detector for wear leveling, but you can potentially use it for other preventive actions as well. Just, for example, kill the application, inform the OS, deprioritize the application. And it's applicable to other wear leveling algorithms as well. Thank you, and I'll be happy to take your questions.
I just have a quick question.
Again. Oh.
For the counters that you're using, were they saturating counters?
They are saturating counters, indeed. Thank you.
Next, we have Adrian Caulfield from the Non-Volatile Systems Lab here, and he'll be talking about Moneta, a high-performance storage array architecture.
Thanks. All right, so I'd like to tell you a little bit about some work that we've been doing at UCSD, trying to understand what impact emerging non-volatile memories like phase change memory and spin torque transfer, even racetrack or memristor, will have on how we architect and build very high-performance SSDs. So we've actually built a prototype SSD that we call Moneta, and we've been looking at what hardware optimizations and software optimizations, as well as what changes to the interface between the two we can make to get very good performance out of these systems. So this work was done with my colleagues Arup Day, Joel Coburn, Todor Mollov, and professors Rajesh Gupta and Stephen Swanson. So if we look at trends in storage, we're really facing a revolution in storage technologies. Starting with hard disk drives, we've had latencies of about 7 milliseconds. Bandwidth was about 2.5 megabytes a second for random accesses, about 4K. But within the last couple of years, we've had very fast PCI Express-based flash SSDs show up. And these give us much better performance, about 68 microseconds for reads, 250 megabytes a second. But we can do even better than that. And with the SSD that I'll show you today, we're able to reduce latencies down to about 12 microseconds. We can get 1.7 gigabytes a second of bandwidth. So this is about a 600 or 700x improvement in performance over hard drives from just a couple of years ago. And if you do the math on this, it works out to about 3x a year performance improvement. And we expect this trend to continue for a little bit while longer. So specifically, if we look at one example of how this is changing things, on this graph, I've broken down latency into several different components: the file system, the operating system, and the hardware component for disk drives, flash, and PCM. And this is on a log scale. So you can see with the disk drives, basically the hardware component is significantly overpowering any of the software latencies that we're experiencing. And so we don't spend a lot of time optimizing our software latencies because it doesn't make much sense. With flash, we're doing a lot better on the hardware latencies, but we still have significant overheads compared to the software components. But when we get down to PCM, the hardware latencies are actually less than some of the software overheads that we're seeing, and so we need to spend a lot more time thinking about how we can reduce those software overheads to take full advantage of these memories. So how do you go about architecting a high-performance SSD? Well, obviously the hardware architecture and the software layers are going to limit your performance, so you have to spend some time there. But it's also critical to think about what the hardware and software interface should look like and how we can co-design that to take advantage of things that when you change both sides, you get much better performance, including increased bandwidth, decreased latencies, and higher concurrency through your driver. So that's the motivation behind our work. I'll take you quickly through what Moneta's architecture looks like, and then we'll look at how we can optimize several of the hardware components as well as the software stack. Then we'll look at some performance numbers, and I'll conclude. So here's what Moneta's architecture looks like. The easiest way to explain this is by walking through a request as it travels through the system. That happens when a PIO request comes from the operating system over our PCI Express connection. From there, it enters a request queue, and when space is available in our scoreboard, we'll remove that and start processing the request. The first thing we do is allocate a transfer buffer, and then issue some DMA requests to fetch data from the host system. Once that comes back, we'll send a message across our ring network to one or more of the PCM memory controllers. And once the data is actually written and durable in memory, we'll send a message back across the ring to the scoreboard, where when we finish the request, we'll set a bit in our tag status register and send an interrupt back to the host system. At that point, the host can read that register and figure out which requests have finished. We can actually track 64 outstanding requests in flight at the same time in our hardware. So the stack on top of this is pretty similar to a lot of other I/O devices. We have the hardware at the bottom that connects to the host system over PCI Express. And then we have Moneta's driver, the operating system's I/O stack, the file system, and then finally the application at the user space level on top of that. So we've designed Moneta to work with any advanced non-volatile memory. Specifically, we're looking for things that have DRAM-like speeds and DRAM-like interfaces. Phase change memory is a good example of this. We expect these kinds of interfaces to come out in the near future, but they do require some wear leveling, as we just heard. And StartGap gives us a way to implement that without too much overhead. And so that's what we do in Moneta. To build Moneta, we've implemented this platform on top of the B3 board originally designed for the RAMP project. And this connects to our host system over PCI Express. The whole design runs at 250 megahertz. And we're actually, in this case, using DDR2 memory to emulate these non-volatile memories that we don't actually have access to yet. And we can do that by adjusting some of the timings in the DDR controller to match the latencies that we expect for PCM. And those latencies are about 50 nanoseconds for reads and 150 nanoseconds for writes. And these are from previous works that have been published in ISCA 2009. So that's what Moneta's architecture looks like. Let's now take a look at some of the optimizations that we've made to the hardware-software interface and the software layer on top of it. So what we found when building Moneta is that optimizing the software is very critical to getting good performance. The first version of our driver that we wrote, we found that the hardware had about 8 microseconds of latency, and the software on top of that was about 13.4 microseconds. So we implemented several optimizations, namely removing the I/O scheduler, which reduces the amount of code that we have to execute, but it also significantly increases the concurrency that we can get passing requests through our driver. Next, we implemented several atomic optimizations. We use all lock-free data structures in our driver, but we've also optimized our hardware interface so that we don't need any locks or memory barriers to protect the accesses talking to the hardware. And finally, for very small requests, we use spin weights waiting for the completions instead of allowing threads to sleep. And this gives us a significant bonus for very small requests. So we're able to cut our software latencies down to about 5 microseconds with these various optimizations, and this is 62% over the baseline driver implementation. If we look at what effect those optimizations have on bandwidth, on this graph, the x-axis is request size in kilobytes from 512 bytes up to 0.5 megabyte. The y-axis is bandwidth in gigabytes a second, and the 2 gigabytes a second line at the top is the ideal bandwidth that we should be able to get over our PCI Express connection. And so you'll see that the bandwidth generally improves as you increase request size, which makes a lot of sense. And then when we hit 64 kilobyte requests, the bandwidth sort of caps out, and this is the actual peak bandwidth that we can get over our connection. So as we implement each of these optimizations, you can see that we're moving the performance up significantly. And this is removing the I/O scheduler. And as I said, this significantly increases our concurrency. And so that's why we get much better performance across the board. When we implemented the atomic operations, including the lock-free data structure and the hardware-software interface, requests over 4 kilobytes in size see significant improvements. But for smaller requests, not having spin weights and being able to complete these requests quickly is limiting our performance. And so when we add in the spin weights, we get the performance improvements for the small requests as well. So what's interesting here is we are actually able to hit about 1,512-byte IOPS. And if we had more PCI Express bandwidth, we would be able to get that same number for a lot of the other request sizes as well. Another interesting characteristic to look at with these very fast storage technologies is that we're actually at a point where we can actually become CPU bound because our I/O devices are a lot faster than we're expecting. And so on this graph, I've plotted the number of Nehalem CPU cores it takes to issue a gigabyte a second of bandwidth with each of our driver implementations. And so if you write a very naive basic driver, you're actually going to need 12 full Nehalem cores to sustain a gigabyte a second of bandwidth to these devices. But after you implement some of the optimizations, you can cut that down to about 3. And obviously, when we add the spin weights back in, we're utilizing more of the CPU cores waiting for requests. And so that's why the performance goes down a little bit for that one. So finally, let's look at some of the hardware architecture changes that we're making. Specifically, one of the things that we'd like to be able to do is make full use of this full duplex PCI Express bandwidth that we have. And so in our first implementation of the hardware, we had a single request queue that would, you queue up your request, you have a large read and then a large write. They process one after the other, and you don't get to make full use of your bandwidth. But if you alternate between allocating buffers for reads and writes and split them up and process them at the same time, you can actually almost double your request performance over the interconnect. Another optimization that we've made is implementing round-robin scheduling. And so this is to handle the case where if you have a very large request followed by lots of small requests, the large request will actually block the small request from executing. And so your throughput isn't as good for the small requests as it could be. So if we implement scheduling where we process just a part of the large request and then allow the smaller request to access and then allow the large request to continue, we can get much better performance. We see about 12x improvement for those small requests without any significant loss in performance for the larger requests. Another thing that's worth noting here is that when you're optimizing your non-volatile memory, whether it's phase change or any of the others, for storage uses, you want to look at a lot of different things than if you were targeting that non-volatile memory at a DRAM replacement type of role. Specifically, if you look at write coalescing, which you would normally do on the DRAM bus, you open a row, you perform several accesses, and then when you move to another row, you'll close that and write the memory and make it durable. In storage uses, we want to make sure that our requests are durable right away, and so we can't make use of that technology as freely. Another concern is how big should the row buffers be? Row buffers are expensive in terms of power. For storage accesses, you want your row buffer to generally match your I/O request size, which in storage is obviously quite a bit larger than the cache line size accesses that you have in DRAM by default. And so you want to make sure that your non-volatile memory has row buffer sizes that match the access pattern that you expect. Another thing with storage arrays is that often you have a lot more internal bandwidth inside your storage array than you have external bandwidth available over PCI Express, whatever connection you're using. And so a lot of the memory is sitting idle a lot of the time, and we can make use of that in various ways. So the bottom line is that you have to think carefully about what you're targeting your non-volatile memory for and how you want to optimize it. So let's just look quickly at some performance numbers for our device for running applications on top of it, as well as some comparisons to other storage technologies. To do this, we have a system that looks like this. It has 5 different storage technologies. We have a FusionIO IO drive. We have a software RAID 0 of flash SSDs. We have a hardware RAID 0 of hard disks. And then we have 2 versions of Moneta. One has a 8x PCI Express link, and the other has a 4x PCI Express link. So if we look at some just very basic I/O performance numbers comparing all of these devices, the trends are about what we'd expect. The hard disks do relatively poorly, but the flash SSDs do a little bit better on top of that, and then the FusionIO device is doing the best out of the flash-based devices. And then Moneta is obviously quite a bit faster. The memory has lower latency, so this makes a lot of sense. If we look at just a couple numbers in particular, and these numbers are looking at performance without a file system, just for raw accesses, for 4 megabyte accesses and 4 kilobyte accesses. And the performance that we see makes sense. Moneta's performance is relatively good for large accesses and small accesses. We don't see a lot of difference. And then for the other devices, the smaller accesses are penalized a little bit more than for the larger accesses. What's interesting is when we add an XFS file system on top of this, most of the devices don't see a significant performance loss from adding the file system on top. But because Moneta has such low latencies, the extra microseconds that the file system adds on top of this are significantly impacting our write performance and throughput. And so this is an example of a place where we have to think very carefully about how we can optimize our software to get rid of a lot of those latencies that we don't necessarily need, that were optimizations for disk drives. And if we can remove those, we should be able to get back a lot of this performance. So finally, if we look at application performance on top of our devices, on the left graph we have a variety of database workloads. And on the right graph we have several applications that are memory hungry, and so we're actually using our devices as backing stores for your page file. And on each of these graphs, the leftmost bar is the raw XDD 4 kilobyte read-write performance from the previous graphs. And so these are all plotted relative to the disk RAID array performance. And the trend looks pretty good as you move from disk to flash-based devices. The raw I/O performance generally matches fairly closely with the application level performance. But when we move to Moneta, a lot of these applications aren't able to take full advantage of the very fast performance that we have compared to what we're able to see on the raw I/O performance. So in conclusion, these very fast emerging non-volatile memories are coming very soon. And we built Moneta to help us understand what impact they'll have on our systems. And we found that optimizing your hardware and software interface is very important for getting the best performance out of these systems. But there are also a lot of other opportunities where we can move optimizations that we have in software down into the hardware to try and get rid of some of those software overheads that I was talking about. But there are also a lot of open questions that still exist about what the architecture should look like, what the non-volatile memories are going to look like, and how we can optimize our systems to work best with these very fast technologies. So thank you, and I'll be happy to take any questions. Yeah.
So you reported 1 million IOs at 512 byte block transfers.
Mm-hmm.
What is the host configuration you need?
The host configuration? So it's a Nehalem machine, 2 processors, so it's got 8 cores with SMT. Just a PCI Express 1x, 8x link. Sorry. Yeah.
You suggested that the storage system should have row buffer locality. Do you actually believe that there's enough locality in storage that overfetching into a row buffer will give you additional performance, or are you going to simply have page conflicts and write everything back immediately?
What I was trying to suggest is that basically the row buffer should match the size of the I/O requests that you're doing, so that you don't have to issue multiple requests to write your data into the array at the same time. And basically, I'm arguing that you shouldn't use write coalescing for these devices because you want the writes to be durable as soon as you've finished accessing. Yeah. So it takes it's a good question. It takes, I think, about half of the machine to keep those IOs going. So the CPU. Yeah, definitely. Yep. Anyway, sure.
Did you do any testing of the Moneta's performance as queue depth varies?
As queue depth varies. Not significantly. I mean, we've looked at different numbers of threads issuing requests, and basically, the more threads you have, the better your performance is going to be until you've run out of processors to run those threads on. But we haven't looked at different numbers of outstanding requests and things like that. Sure.
What not-free data structures did you implement?
So basically, we have a structure for managing tags. And assigning tags to requests as they pass through the driver. And so optimizing. Sorry, what? Is that a hash table? It's not a hash table. It's just a basic. You can think of it as a queue basically. As each request comes in, you want to assign a tag to each request. But you want to make sure that you're not, having concurrency issues across all of your cores, fighting for available tags and things like that.
I had a question. Thanks. You mentioned getting rid of the I/O scheduler, but then later in the talk you were also talking about scheduling, in particular like interleaving small and large I/Os. Plus, I think you were doing write coalescing. So, how did you both eliminate it but still keep it?
So the I/O scheduling that happens in the kernel is basically targeted at disk. So we're looking at how we can turn. In that case, you want to take random accesses and turn them into sequential accesses whenever possible and group things together. So it's the scheduling that's happening is quite different than what we want for balancing bandwidth or making sure that we can get full duplex PCIe links and things like that. So the main problem with the I/O scheduler in the kernel is that you have to write all of your requests into a queue, and then they get passed to the driver one at a time. And so at that point, you've limited yourself to essentially a single CPU core for issuing requests, which doesn't let you have the bandwidth that you need. Yeah, I mean, that would improve things. But again, the more code that you're executing, the more software overheads you're going to have.
Okay, I think
we can take it offline.
Yes, we should take additional questions offline. Let's thank the speaker.
Yep.
And our next speaker is David Nellans from FusionIO, talking about a new primitive PTRIM and how that would be used.
Hi, my name is Dave Nellans. I'm from FusionIO, where I'm a senior software engineer working on higher level things within the FTL stack. And today I wanted to talk to you about some new FTL primitives that we're proposing may be useful for applications to access directly instead of through the block layer. So we've heard a lot of talk here, terms non-volatile memory. And so what that means is a bit confusing in the terms of storage class memory. We have non-volatile things that happen to be on the memory bus. We have volatile things that happen to be on the storage bus. And we have things that are just historically there and you can access via a char device if you really want to. But I think as application programmers, the real key is that if we go in to write something today, all of us know there are only two interfaces. One is memory and one is storage. And in this world, sort of the storage interface and the memory interface really define the technology we're using, no matter what we're calling it. And so storage is typically defined by being block-oriented. It has a persistent namespace, namely the logical block addresses. And for the most part, applications can physically address this. Memory, on the other hand, is word-oriented. It has a volatile namespace. When it comes back, you don't know what's there. And it tends to be virtually addressed. You access things via malloc, moving through the virtual memory address space. And so memory we tend to think of as being something that's good for random accesses. And storage historically has been sequentially accessed. That line's getting blurred as we move into Flash and PCM, obviously. But data persistence, on the other hand, only exists in storage today, right? Even when we talk about using phase change memory, aside from some proposals we've seen here over the last year or two, it's still being used as a volatile memory. It just happens to be higher density. And so today we're going to talk a little bit about potentially blurring these lines on the storage side. So the key thing that we want to think about is that storage is typically physically addressed, whereas memory is virtually addressed. And so what does this really mean?
Well, in the traditional storage stack, applications and database management systems can talk to a block device directly, or they can go through a file system. But the block device is implemented as essentially a one-to-one relationship on top of the physical block addresses. Inside traditional hard drives, there is some remapping for bad sectors, but it's not an any-to-any mapping. It's typically viewed as a one-to-one. As we move into the storage stack with flash translation layers, though, we've really had a fundamental shift. We're now virtually addressing between logical block addresses and physical block addresses. We have essentially an any-to-any mapping, depending on your FTL implementation, for a variety of reasons. So what are some of those reasons? We have peculiarities of the technology is the number one reason we've chosen to do this. Right? We have limited cell endurance, and so we need to be able to do wear leveling across these things. So the physical address that's underlying a logical block address has to be able to change transparently without the application knowing about it. We also have to work around these block operations, bulk erase versus writes. Depending on the technology, these parameters may change. We also have the asymmetric read-write erase operations. We don't want to have to erase something before we overwrite it. And so we implement virtual addressing to allow that address to hide the fact that we're changing the location under the hood. However, even though we have this virtual addressing, storage is still essentially viewed as physically addressable. We read and write to logical block addresses, which have a fixed address. Right? They don't change. If you write to block 4 will still be there next time you write it or read it, and it'll have the same thing in it. We don't do something like a storage allocate, then we can read and write, and then we free it. Those interfaces simply don't exist today. And so the proposal that we're making is that we should probably start thinking about storage as something that is virtually addressed, as a first-class primitive. We want to provide APIs that allow you to query into the FTL to find out whether blocks are mapped or not and other properties about them. So the reason we want to expose this, not only for performance querying, is that it allows us, in the case of this talk, to eliminate redundant mappings within the stack. So currently, your application may have some sort of tracking, a hash map down to a block address that is a file system logical block. The file system, in turn, may have a logical block that it's mapping to an LBA via extents. And then the flash translation layer is doing the same thing, mapping a logical block address onto a physical block address in the NAND. So we propose that by exposing things from the FTL all the way up the stack, potentially we can collapse that tracking information down. So what's the first primitive that we really need to expose to allow the notion that this is a virtually addressed piece of storage? So in about 2009, 2010, the TRIM operation was proposed and has now been implemented in both Windows and Linux that allows you to unmap a block range. Right? And so when you're doing a read, a write, you can now trim something so that the block is unmapped within the FTL, but next time you read it, it will still be there for you. The reason TRIM was implemented is to provide a hint to the FTL that it doesn't need to track this data anymore in its virtually addressed mapping. And so this helps improve both wear leveling and write performance through allowing a larger free block pool that can then be used for write buffering, improved wear leveling. So the trim operation, on first glance, appears to be fairly analogous to a free operation in the virtual memory subsystem. But it's not quite there, which is a distinction we really want to make. So trim on a block range is good because it allows no data DMA to happen. I should say, it doesn't require data DMA to happen. You simply provide a logical block address, and it removes the mapping in the FTL. You don't have to transfer zeros over the data bus to overwrite data and then try and assume that zeroed blocks are free or something like that. So it's a performance optimization. Write after trim is a well-specified operation. If you write something after a trim operation, you're going to have the write that was into that location available on your next read. The problem with the trim operation as it exists today is that the read after trim operation is essentially underspecified. If you perform a trim and then immediately perform a read, you actually have no guarantee on what's going to come back. You might get zeros back, you might get old data back, you may even get new data from a remapping that's happened under the hood. Or a combination of these. Multiple calls to a read after a trim operation without a write intervening can provide different behavior because the FTL is under no obligation to actually implement the trim immediately or at any time in the future. Internal testing at Fusion has shown that there are devices out there that claim to be trim capable that actually don't implement trim in any noticeable way for a performance improvement, in fact. So one other issue with trim is that it's not currently power cut safe. If a trim is issued and the block is zeroed, allowed to be used for garbage collection, the power cut happens on the machine, it comes back up, and you read the same block. Potentially, you can now have data returned that wasn't there prior to power cut. So in this talk, we're proposing something that we call persistent trim. And so persistent trim has fairly similar semantics to the normal trim operation in that we have no data DMA required, addresses only, and the write after trim, there's no change. It's well specified. We're now defining the read after trim, however, as being non-reorderable and immediately executed. So this means that anytime you issue a read directly after your trim, you're going to get zeros back. So you can think of this essentially as the read after trim as being a reallocation to the corresponding free. And persistent trim has to be power cut safe, right? If you want to have that specification well defined. The problems with persistent trim, as you can imagine, is we can't cache this in RAM. It can't be in the forward mapping only. So we actually have to touch on media data, particularly in the case of power flush. So it has the potential to be slower than a normal trim operation. And so we need to use trim and persistent trim wisely because they're fundamentally two different operations. One is simply a performance optimization, and the second is an operation that you can use to determine existence in a mapping table, which is where we're going today. So we've now provided two functions that allow you to unmap data. So what are the semantics of the storage system? Currently, a read, let's assume a freshly formatted device, no data the application knows about. A read is really performing an FTL allocation before doing that read within the virtual mapping. A write also is performing that same allocation. A trim provides the hint for block unmapping, and a persistent trim provides an immediate directive. And so trim and a persistent trim aren't all that useful in isolation because read and write are the only other options you have to get to things. So we propose two other interfaces. One specifically is exists, which takes an LBA and will simply tell you whether this has been mapped or not. Right? So now you have the notion of, has this been unmapped or does this exist in the mapping already? The other thing that you might want to do is provide a nameless write. And so instead of providing the logical block address for your write, it simply it takes an object size and space and will return an allocation range somewhere in the logical block range for your application. So the combination of these three operations allow you to do some interesting things at the application level. And so we're really focused here on reducing redundancy, right? Database management systems and file systems maintain this virtual to physical addressing. And this is for convenience and access control, right? It allows us to move things around. It allows us to provide protection. The flash translation layer is really the first change in sort of the storage system that we must maintain this mapping in isolation. Applications can bypass the file system and use a block device directly if they want, but the flash translation layer has no such option. So the insight here is that we should allow the applications to track virtual to physical addresses using the FTL essentially as a block heap manager. And this works because virtual addresses are cheap. right? Just like in virtual memory, virtual addressing is cheap, physical blocks are expensive, so we can have large use of virtual addresses in a sparse address space potentially, and only allocate things on demand. So one application that drove the use of development of these interfaces at Fusion was the notion of doing block caching. So hopefully some of you are familiar with the open source project FlashCache, which takes blocks off of a traditional hard drive and caches the most recently used ones in a SSD or NAND flash. And so FlashCache maintains its own mapping layer from the flash block to the hard drive block so that it knows whether to look things up for a cache hit, where then it goes to the FTL, which then performs a logical to physical translation, or on a cache miss, it simply goes to the backing store, which then has a one-to-one mapping down to the physical address on drive. So the mapping overhead that's required for block caching in FlashCache is about 4.8 gigs of in-memory data per 100 gigs of data on the drive. So currently, Fusion is selling a 5.2 terabyte device, which means that if companies or people want to be using block caching to a large device, they're going to need to buy a machine that has at least 256 gigs of RAM simply to use that. That's just not feasible, right? Everyone realizes that you're trying to minimize costs by doing block caching, and so to have to buy a 256 gig machine of RAM makes this a non-starter. So using these interfaces and the notion of sparseness, Fusion has developed our own cache mapping solution that we're calling Direct Cache. And so it simply uses the exist and persistent TRIM interfaces to use the FTL as the block mapping. If the FTL is implementing a sparse mapping equivalent to the full size of the backing store device, we simply need to do a write into the FTL to provide an insertion at the appropriate cache address. We can look things up by looking for an exist. We don't actually have to touch the media. This is an on-memory map. And then for eviction, we can simply issue a persistent trim. In this case, trim wouldn't be sufficient because it's a hint, not a directive. And so we could potentially trim something that after a power cut, we could come back and we'd have an inconsistent state between the cache and the backing store. And so using this sparse interface, we're able to implement a cache of essentially any size with simply a fixed overhead of about 100 megabytes of metadata to maintain some tracking information in terms of bindings and other things. So what are some other application use cases for these APIs? Well, Direct Cache is the first one that we developed them for, which will be coming out March 22nd of this month. And we have some others that are interesting as well. So DirectFS, which was a publication in FAST 2010, was an FTL integrated file system. Instead of having to keep track of blocks and extents at the file system layer, perhaps we can integrate these more closely within the FTL. Key value stores, which are a hot topic here, are potentially other things that could be integrated into the FTL. Depending on the object size and other things, there may be games that we have to play, and that's something we're actively working on. Object-based storage could certainly be implemented on top of this as well. The key here is to try and reduce those redundant mappings to save space going forward. So what are our conclusions? Storage is now virtually addressed whether we want to know it or not. And so we're proposing that we should accept that it's virtually addressed and implement new interfaces that are natively supported within the FTL. The key here is that we want backwards compatibility with standard block storage. Proposing new interfaces that are neither memory nor storage are very hard to get industry adoption on. And so the PTRIM plus exists as well as TRIM are fundamentally still compatible with the standard block read and write. And if an application doesn't choose to use these, we operate as a normal block device. So one of the questions that we're trying to figure out is this potentially a step forward in a semantic towards a storage class memory. Whether that memory is byte addressable or block addressable, we need to come up with the allocation semantics of how we're going to allocate, free, and track these things. And so there are other FTL operations that we're investigating that we can potentially natively support. Specifically, we published a paper at HPCA just a month ago about an atomic write primitive that uses the virtual mapping as well to provide collapsing of database management systems. And so Fusion's very interested in talking to researchers in all areas on what the application use cases they'd like to see being collapsed into the FTL to save things. As storage class memory starts moving into a faster latency, the interfaces really aren't changing right now. And so providing those additional interfaces, there's a lot of interesting work to be done over the next couple of years. And I'll take any questions. Thank you. The use case for allocate. So currently, read is in the storage system. Both read and write are essentially an allocate operation. So to not break backwards compatibility, we still have to allow that. You can imagine that there's another primitive out there called pre-allocate, right? Which will reserve a range for you instead of having to do it via write immediately to make sure that you can get a contiguous range or a block of ranges. But the fact that read and write today essentially perform the allocate on operation is the only reason that we're maintaining that compatibility.
Well, you put that the definition would be forced to zeros of the data, so reading it doesn't have to do an allocation if an unallocated always returns zeros.
Yeah, so it'll do the allocate. We don't have to do an on media read to do that. Right? The forward map can say, oh, this has been unmapped. But the read operation fundamentally returns something. And so that's the difference. We could do a pre-allocate that returns, yes, you've got your blocks and returns no data.
So are you proposing that the read would do a pre-allocate?
Yes. In this case, for compatibility, we're saying that a read operation is still just returning zeros as opposed to old data or data that's been remapped somewhere else.
Are there any other questions? Okay, let's thank. Oh, yes.
So, do you think these new primitives apply to other SSDs as well?
Absolutely. The fact that Fusion is sort of proposing these, unless we can gain industry adoption across all SSDs, this really won't go anywhere. Internally, we've implemented these so that we have function calls to them. The next step that we're really working on is working with Linux maintainers to try and plumb these up through the virtual block device so that any SSD potentially can implement these things.
Okay, let's thank the speaker again. And next we have Clinton Smullen from University of Virginia, who's going to be talking about spin torque transfer memory. Once this finishes warming up. Okay.
All right, so we've seen some here about some flash-based solutions and some PCM-based solutions, sort of slotting in for the third technology flavor of the year. I'm going to talk a bit about STT-RAM and how it can work with these other memory technologies, and it maybe even displace SRAM and DRAM, to cover the entire memory and storage hierarchy with non-volatile memory. So we've already seen sort of the past couple of days sort of the details about how STT-RAM works. So right here I'm just going to go over some of the benefits and drawbacks that it has compared to other technologies. So it is CMOS compatible like PCM, so you can integrate it on die. You can easily combine it with a controller and so on and so forth. And of course it has no leakage into the storage element because it's non-volatile. And you get extremely fast reads. The drawbacks, of course, you have slow writes, not as slow as flash. But maybe on the speed of DRAM, perhaps quite a bit faster than PCM. And of course, there's high write energy, and it's not as dense as a commodity DRAM type solution. So first, we're going to start in the disk side of the system. So flash-based SSDs, as we've previously seen from the past two talks, they provide massively improved performance over hard disk drives. One of the big issues, however, is that writes are 10 times slower than reads. And so, whereas with a hard disk, you have sort of a somewhat consistently slow performance, with the flash-based SSDs, you now have this much more inconsistent performance. In fact, between random workloads and sequential workloads, you can have significantly significantly large differences in the performance there between the reads and writes, whether they're random or sequential. And the write endurance is only getting worse as we sort of push the cells smaller and smaller, and the number of electrons get even smaller. And so what we're looking at here is that though STT-RAM is not dense enough to replace the flash, we can actually use it to build what we call a merge cache to augment the flash. So the simple idea here is this. We have this flash translation layer that other people have talked about, and this sort of masks the physical block mapping. So we actually have the choice now by adding a new table, the MTL, the merge cache translation layer. You can allocate blocks in the STT-RAM rather than in the flash. So the policy is going to decide when you get a request to write some data, you decide, is it going to the flash blocks or are we going to send it to the STT-RAM? We tried a few different policies, and the IGCC paper goes over that. But what it turns out is just because the latency difference, the write latency difference between flash and STT is so enormous, it is always better to write to the merge cache and just evict on demand. So what we really try to do, and why it's called a merge cache, is that we're trying to coalesce writes to a specific page of flash memory so that once we've actually have to evict it from the merge cache, you're writing entire pages, if possible, rather than writing single sectors at a time. For most workloads, the actual data stream, this doesn't help, but it does help with like the file system metadata. Like if you have a log file for a database system, you end up with these trailing sectors on the trailing edge of the log writes that you have to get to the disk, but are suboptimal from a standpoint of flash. So one of the nice things here, it would be great if we could, of course, change the semantics and sort of make our applications aware of what's going on. But in this case, with this design, we're not actually changing anything about the block interface. We're able to continue using this hard disk-based assumption of sectors or of whatever size you want, but the merge cache is able to sort of ameliorate some of these disadvantages that flash introduces. So I'm not going to go into details of the results and sort of the breakdown of the different policies we looked at. But overall, what we have here is there's a baseline SSD performance. We're using a block-based or page-based FTL, sort of very granular, so assuming the entire FTL is being held by default in DRAM. And then going into the write buffer and then the write buffer with some caching and prefetching, these are schemes where both the FTL and the merge cache are co-located in a 64 megabyte block of STT-RAM. So a bit less, this is for a 30 gigabyte flash storage, and so a bit less than half of that 64 megabytes is used by the FTL, leaving around like 34, 35 megabytes for the merge cache. What you can see is across the board, this is the normalized average response time for some enterprise traces collected from Microsoft Research. It's just simply by doing the write buffering, you can reduce the response time on average by over 75%, and by also using the merge cache to do some selective caching and prefetching. And these are the scenarios where with Flash, you are going to read, say, one sector of data. This is all the application is requested, but you're going to get the entire page anyways. So why not just take that page, and if you have some free space in the merge cache, go ahead and allocate it. So you're not paying any extra cost to read the Flash. You're just simply giving up some of your merge cache capacity. That always does pretty well. The prefetching is simply using the notion that it's very frequent you have a streaming type application, and they're going to come back a little while later and request the next page, and we're just going to go ahead and fetch that as well, and also load it in the merge cache if we have some free space. Of course, the prefetching is going to add potential cost because you're interfering with the existing requests to Flash. And one of the nice things here, we didn't really look at a detailed endurance model, but what we did see is for the durations of these traces, it did reduce or even eliminate the requirement to do erasures on the Flash media. So stepping up above the storage, STT-RAM, it's not as dense as DRAM. And so like Moen was talking about, PCM has the potential, particularly with MLC, to be significantly more dense than DRAM. And so STT-RAM doesn't have the potential yet to replace the DRAM, but you could actually augment the PCM to build a reliable, fully non-volatile memory system. Of course, in the keynote today, we were discussing, what this means for the applications is a completely different question. So moving even a bit higher above that, the extremely high endurance of STT-RAM, this makes it possible to use on-die. And one of the really nice things here is that you can tune the write latency by increasing the size of your access transistor and taking less time. In other words, you have much faster writes. Or if you shrink the size of that access transistor, you can get much better density, but of course you're giving up performance to do that. So right here, what we'd really like is a truly universal memory. And this would mean that we could use it everywhere in both the storage and the memory hierarchy. And that's what the outer boundary on this figure here represents. So SRAM, of course, has extremely high performance, extremely high endurance, but it suffers in all the other respects. I mean, you can do optimization to improve this, but you have to always give something up. Roughly the area covered by SRAM is pretty much always going to be the same no matter what you do. For a storage class STT-RAM, this is a type of device designed to hold data for, say, 10 years or more. You're getting a really high retention time, but you really can't approach the performance or the endurance necessarily of SRAM, but you are actually doing better in all these other metrics. And so the proposal we made at HCCA was that by reducing the area of the MTJ, you're giving up this retention time, but you're able to improve all the other metrics at the same time. So in use in storage, if you're trying to replace flash, maybe even in main memory, if you're trying to replace DRAM, PCM, this is not the best solution. But on die, the lifetime of data is usually significantly less than, say, even a day or a second, or even a fraction of a second. So this could be OK. So here's an example of design of a 1 megabyte memory using STT-RAM. On the x-axis, this is the MTJ write time, so also called the write pulse width. And so, for instance, if you take 1 nanosecond MTJ write time, this means you're holding that write current for an entire nanosecond on top of all the latency you had to pay, peripheral latencies you had to pay to get to the cell itself. These are using cacti, so for a similar SRAM design, it's in the about a 4-cycle range here, because we're sort of gradiating the y-axis by 4 gigahertz clock frequency. What you can see here is that if you simply push the write down to the minimum possible value, not only are you significantly slower than the SRAM design, you're doing worse than you could be doing. And so it's necessary to pay attention to what you're doing. So what you might try to do is a write-optimized design, and you're trying to get as good a write performance as you can get. Of course, for these curves, what you can see is that you can never actually get your write latency to be any less than 2 cycles slower than your SRAM designs. And at the same time, you have an order of magnitude more write energy, and your area is even bigger than the SRAM-based design. This is a possible replacement, but it doesn't seem very good. The only thing we're really winning here is the leakage power. However, if we move farther out there, we're going to give up some of that write performance. Writes are now 6 times slower, but we can actually get faster reads. Our write energy is down to only 5 times more, and we're actually half the area now. So there's this design space, even before you looked at giving up the retention time, of different choices you can make. And so this is actually a curve similar to what the grandest guy showed, except I don't have numbers here. But basically, the limiting factor with STT-RAM performance and even the density is the amount of energy it takes to switch the state of the MTJ. So if we have some mechanism, it doesn't really matter what it is, you can improve the magnetic materials, you can change the area, you can change the thickness, all these different parameters. If you can reduce this write energy, there's a few different things you can use this for to take advantage of. So if you keep the write time the same and just sort of reduce the write energy, you just get a more compact array. So you're going to have higher density, lower write energy, and your read latencies and your write latencies are going to improve a little bit. Alternatively, you could actually sort of keep the write energy the same, but now push that write time down, thereby improving your write latency. The thing we've actually seen, though, is that the peripheral overheads are really large because of the currents involved. And so it's usually better to sort of fall somewhere in the middle, where you're maybe speeding up the write time a little bit, but for the most part, you're just taking the density and the latency improvements that come with it. So talking about how we're relaxing the retention time here, we're having the MTJ's area. This is the cross-sectional area of the free layer for an in-plane magnetic material. So the big thing here, sort of as the grandest guy talked yesterday, the thermal stability is proportionate to the area in addition to all the magnetic and the thickness parameters and so on and so forth. And so what this does is, so if you have sort of a rough retention time model such as this, which has been previously published, storage class retention, 10 years plus, this starts at delta, has to be at least 42 with error correction and so on and so forth, and sort of high temperatures you need much higher. But if you were to have this minimum value, your retention time has gone from 10 years or more to now 1 second. And on the same time, when you're on die, you're going to have to deal with higher temperatures. And so that a delta of 42 for 300K room temperature is only 36 at 350K. And so this is taking you from 10 years now down to months. But going back to this example, we can sort of see what kind of benefits we can get. So what we're looking at here is a feature size of 32 nanometers. And so our baseline cell, it has that delta of 42 at room temperature, sort of the minimum possible storage class design. And so at the elevated temperature of 350K, it only has months of retention in this on-die scenario. A slightly reduced retention time area, which has a 1 second retention time, is 19F squared. And ultimately, we have this ultra-low retention 10F squared design, which only has 56 microseconds of retention. What this gets us, though, is where with the sort of minimum storage class design, we could never do better than 2 cycles worse than SRAM. We can now close that gap up to only 1 cycle worse for both the 19 and 10F squared designs. In terms of write energy, the 11x became the 5x. And this is the same 5x that we saw before when we went for the read-optimized design, which has the 6 cycle slower writes. Simply by reducing the area, we get that same write energy while keeping a fast write latency. Going to 10F squared, of course, it's half again what that 19F squared was. And the area, of course, is just decreasing. This is really because there's possible to push that write time down to sort of force the performance to be higher, but the currents involved still, they're very large. And so in general, it's more optimal to sort of take the latency savings you get from shrinking your array than it is to try to push that even further. And one of the nice things actually here is that 10F squared design, even for the write optimized point, actually has 1 cycle lower read latency than the SRAM design. So looking into the impact on replacing the entire cache hierarchy for a Nellans-style quad-core processor, what one can see is that you give up a fair amount of performance, up to 20% for certain workloads on average. This is not quite as bad. But the real problem that we saw there is it was actually because of the L1 data cache. And that latency is really coming into play. At the level of the L2 and the L3, where we were really able to get read latency improvements, they actually had a positive benefit on performance. And so you give up some of the energy savings by reverting the L1 caches back to SRAM, but it is a possible knob one can do. Sort of switching over to looking at sort of the total energy consumption here, we've broken it down into the read energy, write energy, the leakage due to the peripheral circuitry, and the cell leakage. And so, of course, for the SRAM designs, these are high-performance designs coming from Cacti. The cell leakage is actually only a small component. In particular, the peripheral leakage for the extremely large 8 megabyte L3 is just consuming a lot of energy. So you could consider that you could sort of use more energy efficient, cut back the leakage for those caches, but at the same time, you have to give up performance in doing that. At the same time, while using the exact same high-performance peripheral circuitry, the STT-RAM designs already have a lower peripheral leakage. If you do those same adaptations by reducing the peripheral leakage to the SRAM and you apply them also to the STT-RAM, your leakage again gets cut down to a 10th, or even actually what we saw as a 30th. So the same optimizations apply no matter what technology you're looking at. It's just the interesting thing with STT-RAM is that as you make these optimizations, you get a new broad spectrum. Either you can now tune the retention time, or even look in between write and read optimizations. Stepping from the 32F squared design to the 19F squared design, you're cutting 40% off your write energy, but your leakage is nominally the same. But once you go all the way to the ultra-low retention, you're getting 20% less both write energy and the leakage. And what this is really showing is that you can play with the optimization of the write time, but ultimately reducing the retention time has a much bigger impact, both for performance and for energy savings. So in doing this, it is necessary to ensure correctness. So particularly at the 56 microsecond retention time level, you're very likely going to need some sort of refresh policy to do that. We did some preliminary evaluations and found it doesn't significantly hurt your performance, and it only slightly increases the energy consumption. Overall, it's still a big win over even storage class STT-RAM. And all of this work dovetails with sort of existing research efforts to try to make the MTJs themselves better, either by changing the designs or the magnetic materials. If you take those enhancements, you can then apply these techniques and get an even better MTJ for use on die. And one of the big things here that's good is that by reducing the necessary current to get a high-performance design, this is actually also going to improve the endurance of these devices for their use in on-die applications. So in conclusion, STT-RAM is extremely versatile. And so it may not replace PCM or flash having the storage or main memory space. It can sort of work with those memories to improve the overall system and to provide some amount of non-volatility in innovative ways. So augmenting flash, you can improve your endurance while also significantly improving your performance. And by relaxing the retention time, you can really make it much more effective for designing on-die caches. Take any questions now.
So if I'm a customer shopping for non-volatile memory, I will either go for one or the other, say PCM or STT-RAM. So what's your thought on the how practical it is for customers to get a system with STT-RAM augmenting PCM?
I think most customers, like let's say your enterprise customer, what you want is a solution that meets your needs. And so whether that solution is based on flash or PCM or STT doesn't actually matter to you as long as it provides the performance, the reliability, so on and so forth. So if the manufacturer can meet your needs by combining technologies, as opposed to doing some much more complicated software solution or whatever, I think the customer is still going to buy it, even though it may be intrinsically somewhat more complicated. I think at the same time, like for instance in the case of the merge caching, because rights to that merge cache are already preserved state and because all the FTL is held in the STT-RAM as well, it sort of simplifies a lot of it makes it automatically atomic. Like once you've updated the FTL, the entire FTL is up to date without having to do a write back to flash.
I think we have time for one more question.
These optimizations, did it do anything to the on-off ratio?
For reads? Yeah. The reads don't change that much. The main issue with the reads is you do have to balance the read voltage. So when the guy from Grandos was talking yesterday, he was talking about trying to get the write voltage down from like 3/4 of a volt to half that. So here we're using a write voltage that's a bit over 1 volt with a read voltage that's only 0.3. So there's a nice gap. However, if you use a much lower read voltage, which you would need to, in the case of that type of design, then the changes these optimizations are going to make in terms of the read currents is going to be really significant, and you could get a lot of sort of problems popping up from that. So for the designs we've done, because they're really high-performance designs, we didn't see any issues. But if you're going for sort of a more low-performance, ultra-high-density type designs, that would be more of a concern.
Okay, let's thank the speaker again.